Let's jump right back into part 2 of our explainer on the Lifeblood system. Last time, we covered the turbine's internal oil circuit. Now we're looking at the generator's completely separate oil system and the terrifying moment when it matters most, a total blackout. What's really interesting here is the perfect contrast between these two environments. Remember the turbine lube oil, or TLO? That needs tough synthetic oil to handle blistering extreme heat. But the generator lube oil, or GLO, is dealing with much cooler sleeve bearings, so it just uses ordinary mineral oil. These two systems are totally isolated. They flow, they protect, but they never, ever mix. Since they're totally separate, they have their own ways of moving that oil around. Now, the generator does have its own shaft-driven pump, but there's a huge catch. That pump only works efficiently when the unit is spinning at full speed. So how on earth do you protect the bearings before this massive machine is going fast enough to pump its own oil? Well, that relies on exactly two 100% redundant AC-driven auxiliary pumps. These are absolutely vital. You literally cannot start up or shut down without them, because they push that mineral oil through the GLO system to build a protective film before the shaft even starts to turn. But here's the crucial question. What happens when disaster strikes? Imagine the turbine is running at full load, feeding the grid, and suddenly, a massive external failure causes a total blackout. We're talking about a complete loss of AC electrical power across the entire plant. Without any warning at all, both of those redundant AC auxiliary pumps we just talked about, instantly dead. Power drops to zero. Let's put that in a perspective with some real numbers. Suddenly, you've got this massive, incredibly heavy generator rotor coasting down from an astonishing 3,600 revolutions per minute. The AC power is gone, the shaft is slowing down, so that main shaft-driven pump is losing efficiency fast, and you have absolutely zero oil pressure being pumped to protect those bearings. The lifeblood has just completely stopped flowing. And the physics here, they're completely unforgiving. Without an immediate backup, that heavy, coasting rotor will violently score its own bearings. And I don't mean it'll happen in a few minutes. I mean in mere seconds. At these insane weights and speeds, metal-on-metal contact for even a fraction of a second destroys a bearing. That thin film of oil is literally the only thing standing between a smoothly running machine and catastrophic scrap metal. Without it, a routine plant trip instantly turns into a multi-million-dollar disaster and weeks of downtime. So this brings us to a do-or-die scenario. Think like a control systems engineer for a second. If you had to protect this bearing during a total blackout with absolutely zero reliance on electrical power, what would you design? Take a second. What kind of backup system actually works when everything with a wire is completely dead? The answer brilliantly illustrates one of the most vital engineering truths you will ever learn about this machine. Dumb and physical will always beat smart and electrical. You know, people naturally assume that backup systems need a smarter, higher-tech solution. They want to add another pump, a fancy new sensor, or complex digital logic. But when the stakes are this high and the power is totally gone, any solution requiring electrical power is guaranteed to fail in the exact scenario it desperately needs to survive. So the elegant rescue here? Pure gravity feed. The engineers solved this by placing elevated rundown tanks directly above the generator. These overhead reservoirs just sit there, storing a set amount of oil during normal operation. When the power cuts out and the pressure drops, gravity simply takes over. There are no electronics to fail, no sensors to misread, and absolutely no dependence on the electrical grid. Honestly, it has no failure mode other than the fundamental laws of physics breaking down, or just running out of oil. Let's break down how this mechanical sequence builds perfectly. Step 1, the plant loses AC power in a blackout. Step 2, those AC auxiliary pumps die instantly. Step 3, the massive generator shaft starts coasting down, losing the pressure from its own shaft-driven pump. And then step 4, exactly when it's needed, the overhead rundown tanks automatically drain their stored oil directly into the bearings via gravity. It is perfectly timed by nature to buy you the exact handful of seconds you need for that rotor to safely come to a complete stop without grinding its bearings into dust. So what's the big takeaway here? If you were explaining this to a new hire on site, you'd point out the beautiful, simple logic of this system. You now know why the GLO system is isolated and uses mineral oil. You get why it relies on redundant AC pumps for startup. But most importantly, you understand the genius of those rundown tanks. Relying on pure gravity ensures survival when everything requiring power fails. It's a great reminder that sometimes the simplest, most physical engineering designs are absolutely the most robust. Okay, so oil protects the inside of the machine, but that leaves us with a provocative question for our next explainer. What protects the outside from salt and soot? And what is the exact temperature line you can never, ever cross without warping the engine permanently? We'll dive into washing the compressor and the limits of thermal shock next time.